Hello folks, this is the last section of chapter 9. It's on section 8, which is about powers of complex numbers. So far we have multiplied and divided complex numbers, but now we're going to talk about what it's like to raise them to a power. So what I want to do is consider this number. Let's do bracket r, open parentheses, times the cosine of theta plus I times the sine of theta, close parentheses, close brackets squared. So for notation's sake, sometimes when you use more than one set of parentheses, you can go to brackets on the outside. So what I want to do is, this is just this is a polar complex number raised to the second power. So what I want to do is expand that number. So I'm going to have r times the cosine of theta plus I times the sine of theta times itself. R cosine theta plus I sine theta, and close everything. Okay, using our rule for multiplying polar complex numbers, we take our numbers out in front, r times r, which will be r squared. And then the rule was that you add together your angles. So in this case, I've got cosine. My angles are the same. They're both alpha. So we do cosine of, I said alpha, I'm sorry, theta plus I times sine of theta plus theta. And this is using our rule that we learned a couple of days ago, or last week, about how to add polar complex numbers together. And then if we simplify our terms a little bit, we'll get r squared times the cosine of theta plus theta is just 2 theta plus I times the sine of 2 theta. So if you look at what we got going on here, you don't have to use brackets, by the way. You can use double parentheses. So if you look at what we have going on here, from the original expression to the final expression, this exponent was applied to the very, very front number as well as dropped in and multiplied by theta each time. So this is a specific example for squaring a complex number. However, we're not going to prove it, but this also works for other powers than 2. Okay, and that is called De Moivre's theorem, capital D-E, capital M-O-I-V-R-E. Okay, and De Moivre's theorem states, open up a bracket, r times the cosine of theta plus I times the sine of theta, close parentheses, close the brackets, let's say to the nth power, so not just squared, but to any power n, could be rewritten as r to the n power, open up a bracket, cosine of n theta plus I times the sine of n theta. Okay, so this is the big takeaway from today. This you will have to know for your test. So let's do a couple of examples. For number 1, I want you to just simplify. Actually, the directions are going to be the same for all of them. So let me just type them. Simplify each expression below. Simplify each expression below. Answer in rectangular form. Answer in rectangular form. So just to recap, y'all, rectangular form is of the form a plus bi. A plus bi. And this is something Mr. Ware and I have caught over the last couple days. When you're answering in this form, we need A and B to be very, very, very distinct numbers, okay? So let's suppose you got down to an answer that was like square root of 3 over 2 plus 1 over 2i. Notice the way this is written right now, I can clearly tell this is A, this part is B, and then of course I is I. You do not want to write this as one fraction altogether. So technically, this statement would be equivalent to square root of 3 plus 1 times I is just I all over 2. Though this statement is equivalent to that, this technically is not considered in rectangular form because A and B are not explicitly separate from I. Okay, so that's the idea of rectangular form. Okay, we're just going to do 3 examples. Example number 1. If I give you, let's open up a big bracket, the square root of 2, open parentheses, times the cosine of negative pi over 4 plus I times the sine of negative pi over 4, close parentheses, close the brackets, all of that to the 5th power. So your job is to simplify this expression, but answer in rectangular form. So the first thing that we want to do is actually raise this to the 5th power. To do so, we're going to simplify using De Morph's theorem. So right now we have what looks like the left side, and we're going to expand it like the right side is. So the first thing we're going to do is raise r to the n power. Well, in this case, our r is the square root of 2, and we're going to raise that n as to the 5th power. So that'll be r to the n out front. Open up our bracket times the cosine of n times theta. So theta is negative pi over 4. So n times theta, I'm going to write mine separately, but you could write them all together you want. That's going to be 5 times negative pi over 4 plus I times the sine of, again, n times theta will be 5 times negative pi over 4. Close parentheses, close parentheses. So what we did just now, this step 1 is using De Morph's theorem to go ahead and expand, or I'll say distribute. It's not really distributing, it's applying that 5 to all of the places throughout the number. Okay, the square root of 2 to the 5th power. If you need to, in order to help you expand that, know that this is the same thing as the square root of 2 times the square root of 2 times square root of 2 times square root of 2 times square root of 2. Open up your bracket times the cosine of, this will be negative 5 pi over 4 plus I times the sine of negative 5 pi over 4. Okay, when we simplify these radicals here, we know the square root of 2 times the square root of 2 is 2. Square root of 2 times square root of 2 is 2. And then we know that that 2 times 2 is 4, and then this loner square root of 2 here will have to stay like that. And then this is going to be times, then we actually want to go ahead and simplify what these numbers are. So if you look at the unit circle, we know that the cosine at negative 5 pi over 4 is going to be negative square root of 2 over 2. So that comes from the unit circle. Plus I times the sine at that angle is going to be a positive square root of 2 over 2. Okay, now notice we're continuing to simplify because we have to answer in rectangular form a plus bi. So we're going to continue simplifying by distributing this 4 square roots of 2 to both of these numbers. So when we do that, we're going to get, and again, technically 4 square root of 2 is over 1. So if we multiply the numerator with numerator, denominator with denominator, we're going to get negative 4, well, let me write it in the order that you're seeing it. 4 square roots of 2 times negative square root of 2, so I'll put that negative out front. All over 1 times 2 is 2. Plus I times 4 square roots of 2 times the square root of 2 all over 2. And then if we simplify this, negative 4 divided by 2 is negative 2. Square root of 2 times square root of 2 is just 2. Plus I times, again, 4 divided by 2 is 2. Square root of 2 times square root of 2 is 2. And then to rearrange this to be rectangular form, we'll say negative 4 plus 4i. This is in the form a plus bi, where those are explicitly separate from each other. So there's one type of example. Another type of example that you might get is something like open parentheses 2 plus 2 square roots of 3i all raised to the 6th power. And I want you to give me your answer, and I should have specified this for the one before, but basically, guys, unless I specify that you can round to the nearest hundredth or whatever, you need to assume that your answer should be exact. And this one I definitely do want it exact as well. Now, this question starts off a little bit different than the last question. Notice the last question I gave you in polar form already, so all you had to do was plug it into De Morph's theorem as it wasn't expanded. This question I'm giving you in rectangular form. So the first thing that you're going to have to do is solve for r and theta in order to convert it to polar form. So if we do that, if you recall, r is equal to the square root of x squared plus y squared. So for us, that's going to be the square root of x is 2 squared plus y is 2 square roots of 3 squared. So then 2 squared is 4. And then 2 square roots of 3 squared is the same thing as 2 square roots of 3 times 2 square roots of 3, which will be the square root of 4, plus, and then, okay, let's see, 2 times 2 is 4, square root of 3 times square root of 3 is just 3, so this would be the square root of 4 plus 12, which is 16, and then we know that the square root of 16 is just 4. So we know r is 4. To find theta, x is greater than 0, so we know that theta is going to equal tangent inverse of y over x, because x is greater than 0. So then we know theta is going to equal tangent inverse of y is 2 square roots of 3 over x is 2. So then 2 over 2 is 1, and then we get theta is equal to tangent inverse of square root of 3. If you can't see it written as is, go ahead and take the tangent of both sides so that it cancels out with tangent inverse. And then you get tangent theta is equal to square root of 3. So what this is asking is where's the slope, or what angle on our unit circle has a slope of square root of 3? And that's why I made you fill that out on your study guide, because if you look at that very quickly in the first quadrant, you get that theta is just equal to pi over 3. Okay, so now you've found r and theta, so now you're going to set up this rectangular number as a polar complex number. In doing so, it's going to look like, open bracket, r is 4, open parentheses, times the cosine of theta is pi over 3, plus I times the sine of pi over 3. And then that whole number is raised to the 6th power. So then if you plug this into De Morph's theorem, the 6 will then apply to all three of those terms. So then we get 4 to the 6th power times the cosine of, it'll be 6 times pi over 3. So remember, this 6 applies to the 4 out front, and then it drops into each of these angles as well. So 6 times pi over 3 plus I times the sine of 6 times pi over 3. And then from here, we're just going to go ahead and keep on simplifying. 4 to the 6th power is 4,096 times, this will be the cosine of 6 over 3 is 2, so that'll be 2 pi, plus I times the sine of 2 pi. So it's going to be 4,096 times the cosine of 2 pi, the x value at 2 pi is 1, plus I times the sine, the y value at 2 pi is 0. So this value cancels, it's 0, and then your final answer is 4,096. So even though, I mean, this technically is in the form a plus bi, but this just means that b is 0 because we can't see it. So we only have a real component to this one. Okay, last example. I want you to simplify. Open parentheses, 3 minus 6i to the 4th power. And when necessary, I want you to round to the nearest hundredth, 2 places beyond the decimal. So similar scenarios number 2, I don't give you the problem in the correct form. I'm giving you the question in a complex rectangular number. So your job first is to figure out r and theta. R is going to be the square root of 3 squared plus negative 6 squared. So it'll be the square root of 9 plus 16, which is going to be, oh, nope, not 16. Negative 6 squared is going to be 36. 9 plus 36 will be square root of 45, which can be reduced because 9 is a factor of 45, and it goes into 45 5 times. The square root of 9 is 3. Okay, so r can be written as 3 square roots of 5. Now, again, when I say round, that's typically, you don't want to round until you have to. We don't have to round the square root of 45. We know that we can simplify that as much. You can probably round here and end up being okay, but I would wait to round to the very, very last possible minute. And then to get theta, we're going to do tangent inverse of y over x, which would be negative 6 over 3. And again, we have x is greater than 0, so we do not need to add pi. When we do that, this is where you're going to go ahead and round. We don't know of any angle, theta, on the unit circle off the top of our heads that has a slope of negative 2. So when you type this in your calculator, you want to ensure that you're in radian mode pretty much this entire test. Then you will get that theta is approximately negative 1.11 as our angle. So then you're going to take these two values for r and theta, and we're going to create a polar complex number. So that's going to be 3 square roots of 5 times the cosine of negative 1.11 plus I times the sine of negative 1.11. And then you want to raise this entire number to the 4th power. So again, if I use de Moivre's theorem, this 4 is going to apply to my number out front and to both of the thetas. So then I get 3 square roots of 5 to the 4th power times the cosine of 4 times negative 1.11 plus I times the sine of 4 times negative 1.11. So then this is going to equal, if you have a hard time understanding what 3 square roots of 5 to the 4th power is, write it all out. 3 square roots of 5 times 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 the cosine of 4 times negative 1.11 will be negative 4.44 plus I times the sine of negative 4.44. And then if we go ahead and multiply these numbers, 3 times 3 is 9, times 3 times 3 is another 9, 9 times 9 is 81. And then square root of 5 times square root of 5 is 5. Square root of 5 times square root of 5 is 5. So that would be times 25. And then this is where we're going to go ahead and round. If we plug in the cosine of negative 4.44, we're going to get about negative 0.27. Plus I times the sine of negative 4.44 will be 0.96. 81 times 25 is 2025. And I'll leave my inside alone. Negative 0.27 times I, or plus I times 0.96. And then we're going to go ahead and distribute this 2025 to both of those terms. So when we do that, this is going to equal about negative 546.75 plus 1944I. Okay, this reminds me, and I'm going to mention it in class, but since you're going to be working on it right after this video anyway, a correction, not really a correction, but just a clarification on your study guide. Since the last page of your study guide page 4, practices this entire lesson. On your study guide, all of your answers are going to be exact, except number 24. So for number 24, you're going to round to the nearest hundredth whenever you need to.